Hello everyone, I hope you're doing well and welcome to AliGorithm. Suppose you wanna cook a crab. For this you have a set of steps like adding the flour to the eggs, mix them together, pour them on the pan and adding sugar before cooking the crab. Well, as you can see, we have a set of tasks to be done where some of them are independent but others require other tasks to be done first. Thus, we need to know where to start, or even better if we could get a recipe or a reset. I mean a valid order of the tasks so we can enjoy cooking while listening to music without worrying about forgetting something. Well, mathematically speaking, this network of dependencies between the tasks can be modeled as a directed acyclic graph or DAG. And what we are looking for is called a topological order of the graph. That is, a valid order of the vertices so no vertex appears before its precedents. Even though it looks easy to find such an order on a crab preparation task graph, the problem became much harder when we have hundreds of thousands of tasks, like assembling a quantum computer, managing dependencies by a compiler, or scheduling tasks for a sparse linear solver. Well, this can be solved with the help of a well-known algorithm of graph theory called depth first search or DFS. Similar to the BFS algorithm described in my previous video, DFS is also an exploring algorithm that navigates through a network. It can also be used to solve a maze and is sometimes faster. So let's discover how it works. Roughly speaking, DFS starts by a starting vertex and then discovers the graph by navigating as deep as possible. It first visits an unvisited neighbor, then its unvisited neighbor, and so on until there is no place to go deeper. Then it backtracks and recursively applies the same process again. This continues until it gets back to the origin and all of the vertices have been visited. Now let's describe it in details. The algorithm uses a well-known data structure called a stack, which operates on a LIFO, last in first out principle. Elements are pushed onto the top of the stack and popped from the top as well. The algorithm begins with a start vertex, say S, by pushing it onto the stack, marking it in yellow to indicate that it has been visited. The algorithm then proceeds to pop the top element from the stack, which is S. Once this element is popped, the algorithm picks one of its unvisited neighbors, say A, and pushes it onto the stack. The algorithm continues by popping the top vertex from the stack, visiting it, and pushing one of its unvisited neighbors onto the stack. If a vertex has no unvisited neighbor, the algorithm backtracks until it finds a vertex with an unvisited neighbor by popping element from the stack. This process is repeated until the stack is empty. So to sum up, the pseudocode of the algorithm can be formally written like this. We may start with the iterative implementation where we start by visiting the vertex S. We add it to the stack, and then while the stack is not empty, we check out the top element U. If it has an unvisited out neighbor V, then we visit V and add it to the stack. Otherwise, U is popped out from the stack. Also, an easier recursive version is known as follow. Simply visit a vertex V and then recursively call the DFS on each of its unvisited neighbors. Both of these two implementations have the same time and space complexity. That's big O of V plus E in time and big O of V in space complexity, where the size of V is the number of vertices and the size of the set of E is the number of edges or arc in the case of directed graphs. Note that the DFS has a variety of applications, like checking out the connectivity of a graph, detecting its cycles, solving maze also, and finding a topological order of a directed acyclic graph. Well, speaking of topological order, let's get back to our graph preparation task graph. Here we have a set of tasks. Let's relabel the vertices for simplicity and apply the DFS on this graph. You can start wherever you want, just write down the vertices in the order of their extraction from the stack. And as you can see, a valid topological order is found. And bon appetit! I hope you guys liked this video. If you have any question, do not hesitate to leave it in the comments below. Yeah, and to subscribe to my channel.